Hi, it turns out All India rank 1 for the biomedical engineering paper in GATE 2020 was just 41.67 out of 100, right? Say compared to 90s out of 100 in other branches. So this raises a lot of questions. Was the biomedical engineering paper so hard? How does the students prepare for the upcoming biomedical engineering exams, right? So in the midst of this, a couple of students asked me if I could provide a video with solved explanation for the GATE Biomedical 2020 question paper. Yes, I'm going to do that. Why do I want to do this? I am very much interested in the subject. I have a doctorate degree. I want to help the students. Moreover, I don't want biomedical engineers to score the least rank in the GATE exam. With that, I suggest you pause the video as I read out the question, try it out, and then proceed to look at the solutions. Question number 1 from the biomedical session. M1 and M2 are the roots of the characteristic equation of a linear second order physical system. Match the nature of the roots with the natural response of the system. So we have M1 and M2, which are the two roots. We have three cases. P is where the roots are real and distinct. Q is where the roots are equal. R is where the roots are complex. And three responses of the system are given. K is where the system is critically damped. L is where the system is over damped. M is where the system is under damped. Okay, this is pretty straightforward. The roots are real and distinct. The solutions will drop down very fast, right? So that corresponds to an over damped system response, right? Similarly, when the roots are complex, the solutions are oscillating. That corresponds to an underdamped case. And of course, when the roots are equal, it lies between these two cases, between overdamped and underdamped. And that case is known as, that fine line is known as critically damped. That corresponds to P is L, Q is K, and R is M. And option C is the right answer. Question number 2. A person is sitting in a chair with feet on the ground. While rising up on his feet, the kinematic motion not occurring is. Okay, hip extension occurs, plantar flexion occurs, knee extension also occurs. The movement that does not occur is hip flexion, which is essentially if you raise a foot and move one of your foot with respect to your hip, okay, that is called hip flexion. That is what does not occur. So the answer is choice C. The equipment that measures elasticity of blood vessels in vivo is. Okay, so rheometers used to measure rheological properties, mostly ex vivo. That's not the case. Thermomechanical analyzer that's used to measure thermal properties, right? Again, that's not useful for elasticity. Dynamical mechanical analyzer, DMA, it's used to measure viscoelastic properties, mostly of polymers. But again, this is not useful in vivo, okay? But using this relation known as Moens-Courtier, okay, it is possible to measure elasticity of blood vessels if we know the dimensions of arteries as well as the thickness. For that reason, if we somehow get good estimates of what the dimensions of the arteries are, it's possible to estimate what the, say, elastic properties of the arteries are in vivo. So the answer here is B. Fourth question. Biomaterials with shape memory effects are not used in. Okay. So the key detail here is that shape memory effect. They are not referring to shape memory alloys that has shape memory effect as well as other properties like superelasticity. They are referring to shape memory effect. Okay. This is the ability to go back and forth between two shapes based on thermal stimulus. That's useful for forming clips. That's also useful for clips that we put in the blood vessels as well as some devices that we use to close the blood vessels, say to prevent emboli from moving from one place to the other. And they are also, in fact, one of the first applications has to do with dental wires. As far as orthopedic total joint replacements go, say something like nickel titanium alloy with super elastic properties might be useful, but shape memory property is not all that useful. So the answer for that is C. Fifth question. The MRI scanner parameter of long T-rep or short T-echo will generate a dash contrast image. I think there is a typo in the question, which is why they said it's MTA, marks to all, right? So had it been, both these parameters can be independently varied. Had this been long T-rep and short T-echo, so this is what the combinations would result in. Short T-rep and short T-echo will give T1 weighted image. Okay. Long T-rep and short T-echo will give proton density weighted image. So had it been and had there been no typos, the answer would have been A, but I think there was a typo and marks is awarded to all choices. Similarly, T2 will be based on long T-echo and long T-rep. Sixth question. In diagnostic X-ray imaging, the following is not a part of primary EM radiation interaction in soft tissue. Okay. So atoms in the soft tissue does absorb X-rays and there is photoelectric effect. Similarly, again the atoms absorb the photons and the electrons go to higher states. There is also Compton scattering. What the electrons do after that differs between these two cases. And there is no characteristic radiation in interaction with soft tissues because this is what happens at the cathode where the X-rays are generated. So this does not happen for sure. And as far as pair production is concerned, most X-ray emissions operate at a lesser energy, right? We need at least like 1.02 million electron volts of energy in order for this to happen. But many X-ray emissions are like rated much lesser than this, say like 150 kilo electron volts. Because of that, though this is possible, but it's not likely. So the correct answer here could be either B or D. My answer would be B, but the official answer is both B as well as D. Seventh question. A 5 MHz ultrasound pulse is used to image a tumor at the depth of 2 cm in a soft tissue. Takes time t for the reflected echo from the tumor to come back to the receiver. Instead, if a 2.5 MHz wave is used, how long will it take for the echo from the same tumor to arrive at the receiver? So essentially pretty much all the information given here is to distract you, right? The ultrasound pulse speed depends on density of the material, propagating material, stiffness of the propagating material, but it does not depend on the frequency of the ultrasound wave itself. For that matter, because the speed does not change, the time it takes to go back and get back does not change, okay? So the time t remains the same, hence the correct answer here is B. Eighth problem. X of s is the Laplace transform of a signal x of t. The Laplace transform of dx by dt, assuming x of 0 is 0 is. Okay, so we have x of t, some signal, its Laplace transform is x of s. And we also assume x of 0, x at time t equal to 0 is 0, initial value is 0. We want Laplace transform of the derivative of x of t, okay. So these are the four options. This is again one of the simplest problems. Just by looking at the answers, we can eliminate two of them, okay. Laplace transform, convert differential equations into algebraic equations. So whenever you take Laplace transform, all these derivatives will disappear. You can directly say C is not an answer. Similarly, this has a derivative, D is not going to be an answer. And in fact, one of the simplest properties of Laplace transform is that Laplace transform of a derivative is s x of s minus x of 0. But because this is 0, Laplace transform of this is A, s x of s. Had the question been Laplace transform of the integral of x of t, right? The solution for this would be B, x of s by s. Again, one of the properties of Laplace transform. So the option here is A. Ninth question. Which of the following are odd functions? We are given four functions, P, Q, R and S. sin t, cos t, sin t plus cos t and sin t cos t, right? I mean, odd function by definition, it's f of minus x is minus f of x, right? What it means is, so let's take some function, okay? So what I have here is a sine function, okay? Now rotate it about the origin by 180 degrees. So we have this function here, rotated by the origin by 180 degrees. We get back the function, right? Whatever in this side rotated by 180 degrees, we get back the original function, okay? This is what this term means, and whenever that is the case, it's an odd function. And what I have here is sin t. So sin t is odd. This function satisfies a different kind of symmetry, right? Take the y-axis, reflect whatever is there in this side about the y-axis. You get back the function, right? Such a function is called an even function. In this case, what I have drawn here is cosine of t, okay? So cos t is not odd function. Sum of an even function and an odd function, that is not going to be odd. So this is not an answer. And sin t cos t is nothing but half of sin 2t. Again, we have a sine function. So this is odd. So the correct answer for this is P and S, which is option C. 10th problem. State space model of a system is given as x dot is matrix times x plus another matrix times u, y is matrix times x. The conditions for the system to be controllable are, it's again one of the simplest problems. I mean, the key is to write down the controllability matrix, and the system is controllable when the controllability matrix has full rank. So what is the controllability matrix? Let's write the system in the standard form, okay? So the standard form, we have x dot as ax plus bu and y is cx plus du. Given this, the controllability matrix is defined as, right, the b corresponding to the standard form, a times b corresponding to the standard form, a square b till a power n minus 1 times b, where n is the dimension of the state, right? In this case, there are two variables here, 1 and 2. So n here is 2. So n minus 1 becomes a power 1. So it stops here with b and ab. This is the controllability matrix. Now the rank of this should be full, which means rank of this should be for the system 2. So let's write down this matrix. In this case, B is this matrix, b comma 0. AB is product of this matrix and this matrix, that is 0 plus AB. So this is a controllability matrix. It needs to have full rank. When will that happen? Both these columns are independent of each other because these two terms are 0. We need B better be not equal to 0. If B is 0, then the rank is less than 1, less than 2. Similarly, AB shouldn't be 0. This implies A is also not equal to 0. So the solution here is B not equal to 0 and A not equal to 0. I think that corresponds to option C in the paper. Question 11 from Biomedical Engineering. In microprocessor systems with memory mapped I/O, which of the following is true? Only I/O devices with internal memory can be interfaced. No, that's not the case. I/O devices can be accessed using in and out instructions. No, that is for the isolated I/O systems. each IO device can be addressed as a memory location. Yeah, that's correct. Arithmetic and logic operations cannot be directly performed with the IO data. No, they can be directly performed. So the correct answer is option C. 12th question. The number of electrodes used in recording standard 12-lead electrocardiogram, that is ECG, is. So number of electrodes used for recording. So we got 3 limb electrodes, the right arm, left arm and left leg. And then in the chest we have 6 precordial electrodes, right? V1, V2, V3, V4, V5, V6. So 6 plus 3, we got 9, and then there is one more. Usually there is an electrode in the right leg which is used as a ground. So in total we have like 10 electrodes, and that corresponds to option D. 13th question. Which of the following is not a part of knee joint? So let's look at a knee joint. So we have the thigh over here and the bone corresponding to that, one of the longest bones, femur, and the bone beneath it is known as the tibia, right? These are connected by cartilages and all that. Then we have a kneecap here, and that's called as patella, right? So these 3 form a part of the knee joint. The thing that doesn't fit into the knee joint is there is this additional bone over here, okay, that is called the fibula. Hence fibula does not belong to the knee joint. The option is D. Okay, 14th question. During a routine stethoscopic examination of the left midclavicular 5th intercostal space, murmurs were noted between first and second heart sound. The possible abnormality among the following could be. Okay, so we have 2 information. One is where is that sound heard? Second, when is the sound heard? So let's look at the where. Okay, so essentially the left midclavicle is in the side of the chest. So we have the rib cage over here, right? So the heart is oriented like this, and the left midclavicular line is somewhere in this region. There, intercostal is nothing but we have all this ribs, right? The spaces in between them are called the intercostal space, and if you count 1, 2, 3, 4, 5, right? Spaces between 5 ribs, you will end up somewhere over here. Usually problems with the mitral valve are heard in this region. Of course, aortic will be at the top, slightly towards the right, pulmonary more top, okay, perhaps almost in the center. Same goes with tricuspid. And so first we know that it's the mitral valve, right? Second, so here I have shown heart sound signals during a heartbeat, okay? So this is almost 1/3 of this length, right? This time length. So this is a systole, that is when the heart pumps. And what we have here is the diastole, right? That's when the heart fills, okay? And mitral regurgitation, essentially the heart tries very hard to pump blood into the whole body through the aorta, but it ends up in the atrium itself, right? It goes back into the atrium, all that hard work. So that is usually heard between the first sound and the second sound, which marks the systole, okay? So based on the information given, it's mitral regurgitation. Had it been second sound and the first sound of the next heartbeat, it would have been there is some blockage in the mitral valve, mitral stenosis, okay? Question 15. The thin filament of a muscle fiber is comprised of. Options include troponin, tropomyosin, actin, titin, myosin. Right? At this point you might wonder the question is a bit nonsensical because a muscle fiber has troponin, tropomyosin, actin, myosin, right? That's not the case. Thin filament of the muscle fiber, right, that has troponin, tropomyosin, actin and myosin? No. Myosin is there in the thick filament. Okay, and then we have this additional titin. So where is titin in? So that's in the elastic filament of the muscle fiber. So all these three belong to the muscle fiber, and the answer is the thin filament has troponin, tropomyosin, actin, which I think is option A. 16th question. It's a question from math. The value of the integral evaluated over the contour C is mod z is 3 by 2 is dash. So we are given this integral, we need to find its value, right? This is again one of the easiest problem from analytical functions, okay, and the answer boils down to applying residue theorem. It says, so given any integral like this, we have a function inside this, right? Okay, so given any integral of such a function, that is going to be sum of residues. That's all the theorem says. In order to use this, we need to understand what are the residues, how to calculate them. Okay, the first question, what are the residues? Okay, so let's look at this given function. Where does this function blow up? Blows up at 2 points. One is when z is 1, this becomes infinity, right? So similarly, when z is 2, the function blows up. Then the question that we need to ask is, in order for this to show up in this summation, okay, the z value should be inside the contour integral. So I have represented mod z is 3 by 2 in the complex plane. Okay, so we have a circle with radius 3 over 2. Z is 1 is somewhere over here, right? Z is 1. And z is 2 is somewhere over here outside the circle. So the only singular point that is inside the circle is z is 1. So for this problem, the summation here becomes one term, which is residue of f of z at z is 1. There is only one singular point inside the contour integral, okay, which is counterclockwise, and only that term shows up in the residue. Okay, now how do we calculate this residue of f of z? That's very simple. Take the singular point z minus 1, multiply that by the function f of z, which is z by z minus 1 into z minus 2, right? Evaluate it at the singular point, z is 1. Okay, this singularity is a simple singularity, so multiplying this will help us get rid of it, and now we can evaluate what z by z minus 2 is at this particular value, which is 1, z is 1 by 1 minus 2, and this becomes minus 1, which is the answer. Okay, it's a very simple problem, and in fact one of the easiest problems from complex numbers, analytical functions. Just make sure you know how to apply the corresponding theorems, in this case the residue theorem. 17th question, again from mathematics. The eigenvalues of a 3 by 3 non-singular matrix P are 1, 2, 3. The trace of matrix P inverse rounded off to 2 decimal places is dash. Okay, very simple problem. All we need to do is use the properties of eigenvalues. Okay, so we have matrix P, okay, and we have P inverse. Let's say the eigenvalues of matrix P are lambda 1, lambda 2 and lambda 3. First thing, okay, so what are the eigenvalues of P inverse? If P is, okay, P is non-singular, turns out to be very simple, 1 over lambda 1, 1 over lambda 2, 1 over lambda 3. So given eigenvalues of this, we can find eigenvalues of this. Okay, how does that help in finding the trace of P inverse? Okay, again answer is very simple, because the trace, right, trace of a matrix is sum of its eigenvalues. Sum of eigenvalues. So here eigenvalues are 1, 2, 3. So here it's 1, 1 by 2, 1 by 3. The trace is nothing but 1 plus 1 by 2 plus 1 by 3. That turns out to be, I think, 1.83. A very simple problem, just application of properties of eigenvalues. Question number 18. The following recursion relation, when started from a finite positive non-zero value, converges to. Okay, so we are given some equation. It's a recursion relation because the new value of xn, that is xn plus 1, depends on its old values, right? Now, if we keep on doing this, what will we end up with? That's a question. It also says we will start with a finite positive non-zero value. Okay. Very simple problem. Okay, but a tip at this point. So whenever there is this problems of this type where you need to fill up a blank, okay, even if you don't know the answer, fill it up. Fill it up. In this case, you know it's supposed to be a number. Fill it up with some number. Okay, because there are no negative marks for these type of questions. Okay, so xn plus 1 is this thing. So when it converges, what will the system satisfy? The new value of that I get in here, okay, will not change. So xn plus 1 will remain in its old value, right? And that is given by this relation over here, xn plus 1 by xn. So essentially when things converge, the old value remains the new, same as the new value. Okay, once using this, just solve for xn using this. Okay, let's do that. This implies xn as half of xn square plus 1 by xn. Okay, simple algebra over here. So the 2 goes to this side, the xn goes to this side, and we can cancel an xn from this side, and this implies xn square is 1, which means xn is plus or minus 1. Okay, and we start off with a finite positive non-zero value. First of all, if we start with 0, this is going to remain 0, right? 0 plus 1 over 0, okay, it's not defined. So we start with a positive value, sum of two positive values, it's always going to remain a positive value. And it will end up with the positive 1, because we started off with a positive value. Always, all these calculations are positive. So the answer for this is plus 1. Or you don't need to enter the plus in the exam, so just 1. Question number 19. In a nuclear imaging system, sodium iodide crystals are used to detect gamma rays of 120 kiloelectron volt. The percentage of gamma rays that will pass through 1 centimeter of sodium iodide crystal, assuming the half value layer of sodium iodide is 0.2 centimeter, is rounded off to 1 decimal place. Okay, so this problem, all we need to know is what does half value layer means. Okay, so let's say this is the sodium iodide crystal. Okay, let's say 100% of the radiation enters in this side, okay, and then it has to exit through this side, and the total length is given as 1 centimeters. All it says is half value layer means that it's 0.2, right? So by the time it crosses 0.2 centimeters, okay, this 50% would have become, this 100% would have become half, which is 50%. Okay, another 0.2 centimeters, it will become half, okay, which is 25%. Another 0.2 centimeters, it becomes 12.5%. Another 0.2 centimeters, it becomes 6.25 centimeters. And finally, the moment it crosses the whole 1 centimeter, it becomes 3.12 something. Okay, so the answer is pretty straightforward. I think it's 3.12. 20th question. The distal end of an endoscope is placed at a distance of 1 mm from the gastrointestinal wall. The refractive indices of the fiber core and cladding are 1.5 and 1.45 respectively. The maximum field of view for the endoscope is dash degrees. Okay, this is an interesting problem because it combines an endoscope part and a fiber optic part. Okay, so let's say this is a fiber optic cable, this is a distal end. Okay, we have the core with refractive index N1 and cladding with the refractive index N2, which is slightly lesser. Okay, and this is a distal end, and any light ray going through it is going to get refracted and then reflected. Okay, and say this is the GI wall, gastrointestinal wall. Okay, so now first thing we need to answer to find the field of view is, what is the angle that is allowed for which the fiber optic cable will still work? That is, we know because the fiber optic cable, when will total internal reflection happen here? When this angle is less than the critical angle. For example, let's say this is a critical angle. Okay, if the light ray enters the cladding at this particular angle, let's say like this, okay, then it will pass through this, in which case the fiber optic cable fails, right? So the angle here should at least be the maximum critical angle, and corresponding to that, the angle at which the light ray enters will be restricted. If it enters at a slightly larger angle, then it will pass through this cladding. Okay, so what is this acceptance angle, or angle at which the fiber optic cable will still work? That has a simple formula. Okay, sin theta A is approximately equal to root of n1 square minus n2 square. So approximately, given that refractive index of air is 1. Okay, so now all we need to do is find theta A, that is the acceptance angle, anything beyond which the light won't get total internally reflected. Okay, and the field of view is just twice this angle. So what is the maximum angle that we can view through here? This is known as the field of view. So this is 2 times theta A. Okay, and this turns out to be 2 times 22.58, which is 45.17. This is the answer. Question 21. 2 inductors with the details given below are wound separately on 2 identical ring type ferromagnetic cores. Okay. Number of turns, gauge of wire, self-inductance for coil 1 and coil 2 are given. The ratio L2 by L1 is. Okay, so we have a ring type ferromagnetic core. There are 2 inductors, right? Okay, and for the first inductor we have n number of turns, gauge of wire is G and inductance is L1. Coil 2, there are 2 turns, gauge of wire is G over 2 and inductance is L2. Okay, and we want L2 over L1, right? So the inductance of a ring type, toroidal inductor is mu naught constant n square, which is square of number of turns in the coil, times h. H is, if we take any cross section, what is the height of that, and if A is the inner radius and B is the outer radius, ln of B over A. Okay, so this is the inductance of a toroid. Okay, and given this, we notice this is proportional to n square. So in this case it's 4n square, and this is proportional to n square. And should gauge of wire matter? Gauge of wire is diameter of wire, actually it doesn't show up in this inductance. Okay, doesn't show up at all. So the ratio of inductance just depends on the number of turns in the coil, ratio of number of turns in the coil, the square of that. So 4n square by n square, which is 4. 22nd question. Two dyes X and Y having concentrations in the ratio 0.25 in identical quartz were subjected to absorption measurements in a spectrophotometer. The estimated ratio of their absorbance is 0.5. The ratio of their molar extinction coefficient is. Okay, this is direct application of Beer-Lambert's law. It says absorbance is equal to molar extinction coefficient, okay, times the concentration times the path length. Okay, so we have two different dyes here, X and Y here. So the path length is fixed, but A and C changes. We want how does the ratio of epsilon varies. Okay, so we have AX is epsilon X CX L, AY is epsilon Y CY L. So epsilon X over epsilon Y is AX by AY times CY by CX. So this is 0.5 times 1 by 0.25. Okay, this is 2. So the answer here is 2. 23rd question. Hydrolysis of one ATP molecule provides an energy of dash kilocalories. Okay, the best reference for this is GATE and Hall's physiology, and it says it's 7.3 kilocalories. But having said that, this is the answer. I'm really surprised that such a memory-based question for a numerical value shows up in the GATE exam. Seriously? 24th question. A 830 nanometer laser Doppler flow meter probe is oriented at an angle of 60 degrees to the flow axis. If the average flow velocity is 3 cm per second, the magnitude of Doppler shift frequency is dash. Okay, so I mean, given some blood vessel and some flow axis, see blood is flowing with a velocity v, we use a Doppler flow over here, sends a signal with frequency ft and gets back a signal with frequency fr. So transmitted and received frequencies. So Doppler shift is essentially the difference between these two, transmitted minus reflected or received, is known as a Doppler shift. That is given by 2 times v, the flow of velocity of flow, v times cos theta, the angle at which the probe is oriented with respect to the flow axis, cos theta, by c, which is the speed of, it's a laser Doppler probe, right? So it's the speed of light times the transmitted frequency. Okay, so based on the information given here, we are given the wavelength of the Doppler flow meter, right? So let's rewrite this a bit. So c is f frequency times lambda, right? So once we do that, these terms, ft is not needed to calculate the Doppler shift. We know v is 3 centimeter per second square, right? So 3 into 10 power minus 2. Cos theta is 0.5, cos 60 is 0.5. Finally, lambda is 830 into 10 power minus 9 nanometers, so 9 meters. And if we calculate this expression, it comes down to 36.14 kilohertz. Yes, this is a formula based question, but given that, I mean, Doppler ultrasound is an Doppler based systems are very important, right? Very significant. It's a good idea to remember a couple of formulas based on that. 25th question. A 100 milliamp single current pulse from a pulse generator is used for artificial pacing of heart at the right ventricle. If the delivered energy does not exceed the fibrillation threshold of 300 microjoules, the safe duration of the pulse that could be applied to the tissue mass having an impedance of 500 ohms is dash microseconds. Okay, the question might look threatening because there is all this artificial pacing, fibrillation threshold and all that. All that they are saying is they are sending an electric current through a resistor, and there is a threshold on the maximum energy that could be applied to the resistor. Okay, so just what is the power dissipated in a resistor, and based on that what is the energy that is delivered to the resistor. That's all the problem that we need to calculate. Okay, so say we have a resistor. Okay, there is a current I flowing and its resistance is R. Okay, we know the power supplied to this is VI. Okay, which is in this case I square R, because both I and R are given. Okay, now instead of power we have to put a limit on the energy. So energy is P times T. Okay, so this is I square RT. This should not exceed 300 into 10 power minus 6 joules, right? At best the time is limited by this. So plug in I square and R, find the value of T. Okay, so I square is 100 milliamps, so it's 0.1 squared, and R is 500. Plug in these values, we get T to be 6 into 10 power minus 5 seconds, that is 60 microseconds. 26th question. The resting potential of a mammalian nerve cell is minus 80 millivolts. A certain drug administered to the body changes the intracellular potassium concentration from 150 millimole per liter to 55 millimole per liter. The nearest value of cell membrane potential after the drug administration, assuming that the external equilibrium of potassium ions does not get changed during the event, is okay. Some gas constant, core body temperature, and Faraday constant are given. The solution depends on application of what is known as the Nernst equation. Okay, essentially intracellular potential inside a cell minus potential outside the cell, extracellular potential, that's given by minus RTZF. R is gas constant, T is temperature. Make sure you substitute temperature in Kelvin. Okay, what is given in 37 degrees Celsius, so convert that plus 270 to 273, I suppose, to get it in Kelvin. Z is the valence. For potassium it's 1, right? It's K plus, so it's 1. F, again Faraday constant is given. Thing is, if you find this constant, this would turn out to be minus 26.17. Okay, so intracellular potential is minus 26.17 ln Ca by Cv. Now use this to find the change in potentials. Okay, so let me write down things clearly. Initially, so the resting potential is minus 80, right? So minus 80 millivolts is say the phi intracellular initially minus phi extracellular, right? Extracellular concentrations doesn't change, so I am supposing phi E remains the same. That's minus 26.17 ln of intracellular potential is 150 millimoles, right? So 150 by C naught. Then after the change, let's say the potential is phi 2. Okay, so this is phi, the new intracellular concentration, phi I2 minus phi E, that's minus 26.17 ln of the new intracellular potential concentration is 55 by C naught. Okay, so this implies take the difference between these two, minus 80 minus phi2 is minus 26.17 ln of 150 by 55. The CE term is it's a constant in both. Extracellular potassium concentration doesn't change, so they will get cancelled. So what we will end up with this, and from this we can calculate phi2 to be minus 53.2, and because 80 is in millivolts, this should be again in millivolts. So just an application of the Nernst equation. Okay, all it says is, I mean, potentials are in general quadratic, right? Because concentration is non-negative, the more appropriate term is ln of, say, the equilibrium value over the new value, or in this case intracellular value minus extracellular value. That's all there is to this. Question number 27. This is one of my favorite questions from the whole paper, and I'm going to discuss it slightly differently. Let me read the question. The arrangement of 4 resistors of equal value in the diaphragm of a physiological pressure measurement catheter is shown below. The applied pressure is observed to cause an increase in length of resistors R2, R4 and an increase in cross-sectional area in resistance R3 and R1. The operation results in an equal change in the values of all 4 resistors, which among the configuration given below should be used to connect the resistors to form a Wheatstone bridge, so that the bridge output voltage is proportional to the change in resistance of individual resistors. Okay, so let me say the answer for this one. Based on the key, the answer for this is, right, only option A, which is only the circuit 1 is the right answer. Only this will give a voltage that's proportional to, let's say, a difference in resistance is X. Only this particular circuit number 1, will give such an voltage. Okay, so having said that, now let's try to go and write the actual potential difference. It's a simple Wheatstone bridge, right? Okay, let's say we have an applied voltage Vi and the measured output voltage is V0. Okay, V0 is nothing but difference between potential here and potential here. Can you find the potential here? Yes, we can use the voltage divider rule, right? R1 by total resistance, R1 plus R2. Similarly, we can write the potential here and we can take the difference between them. In fact, so V0 will be difference between 2 voltages. First is take Vi, split it in the ratio of R1 plus X by the whole resistance, right? R1 plus X plus R2 plus X, where X is a change in resistance. It's equal for all 4 values, so I have it as X for all these resistors. So this point, this voltage minus this voltage, which is R4 plus X by whole resistance, R4 plus X plus R3 plus X, right? Agreed? Okay, and that times, of course, the voltage that get divided is the input voltage Vi. Okay, at this stage, okay, this expression looks a bit slightly nasty. It's not going to lead you anywhere. Let's introduce some assumptions. That is, let's say the base value of all 4 resistances are the same. That's R1 equals R2 equals R3 equals R4. Okay, this is a very good assumption because that's how, in fact, this strain gauge based Wheatstone bridges are designed. So I'm going to remove these differences: R1, R2, R2, R4, R4, R3. So we have R plus X by R plus X, R plus X, R plus X by R plus X, R plus X. Okay, one way to justify this assumption is, given any 4 resistance, this circuit should work. I might as well pick special case where all resistances are equal. Okay, now we notice, at least in this special case, V0 becomes 0, right? So the difference between this and this is 0. So we end up with this absurd situation that for the circuit 1, V0 is 0. Then there is something going wrong, right? But the answer, correct answer, in fact, is this particular circuit. So where are we going wrong? Pause this video, take a moment to think about it. There is some issue, some mistake that I have deliberately made here. That is the key to the answer. Okay? So the answer is this.
in actual this, whenever four resistors are arranged in a diaphragm, okay, R4 and R2 change their length, right? Increase their length. So let's say the change in values is X, okay. These R1 and R2 usually are arranged perpendicular to R4 and R2. So if they increase in length, they increase in cross section, right? Area. When cross sectional area increases, their length actually decreases. This is like the Poisson's ratio, right? So if their length increases, length of R2 and R1 and R3 should decrease. So this should be minus X, and of course R1 is plus X. Even though values change by the same amount, for R4 and R2 they increase, for R1 and R3 they decrease. So let's go back and make that correction over here. So R1 minus X, okay, R1 minus X and R2 plus X. Then R4 plus X, R4 plus X and R1 minus X, okay. So this is a correct expression for the output voltage because two of them will increase resistances, the other two will decrease, but by the same amount. Okay, now having said this, now this becomes a much easier expression. So this is just 2R in the denominator, 2R in the denominator. We notice what we have in the numerator is actually the R's will get cancelled, minus 2X by 2R in the denominator. So we get a voltage that's proportional to X for circuit number 1. Okay, this is a very tricky problem. Try to look at the explanation again and try to explain why circuit 2 is not the right answer. Okay. 28th question. For the given input voltage Vin is 10 sin 2 pi t to the functional circuit shown below, the output signal will be. We are given 4 options. The correct option is option D. Okay. So essentially we are given a circuit like this, functional circuit, and we give a V in which is 10 sin 2 pi t. We want to know what the voltage here at this output would be. Again, because the circuit might look complicated, this question might be threatening, but again, this is very simple if you know how to actually deal with this. First thing is, first rule, anything to do with such complicated circuits, divide and conquer. Identify parts that perform different functionalities. Okay, so I'm going to break this circuit into 2 here and another circuit over here. So if you notice, this whole circuit over here, right, that is a comparator. What it's going to do is, so the input is drawn over here, okay, and if you notice the voltage at this terminal is 0, right? So wherever the input voltage is above 0, which is the reference here, it's going to give a saturation value for this op amp. Sorry. So if you notice from here till here, input voltage is above 0. So from here to here, the output at this location is going to be this. And then when it touches this particular point, input voltage becomes 0, which is less than the reference, becomes negative, which is less than the reference. So this thing goes to this side and saturated at minus 12 till this point. Okay, so the first part of the circuit is a comparator. It says compared to a reference whether it's higher or lower. In this part it's higher compared to 0, in this part it's lower compared to 0. This circuit, okay, it's just a differentiator. Whatever we throw in here, it's going to differentiate that and give the signal. Again, that's very simple. So you notice anywhere over here it's a constant, right? Where does the slope change for this? Slope changes here. There are sharp changes over here. And there is going to be a negative sign. So if there is a positive slope change, there is going to be a negative spike. Then it gets back to 0. and slope doesn't change here, so there is no derivative in this location. Then slope becomes negative, okay, there is a positive spike and things get back to 0. First circuit is a comparator at this point, from here to here it's a differentiator, so we get this curve. And to just okay, so option A is, if it were till this point, option A is correct. Option B is an integrator. Had the capacitor were replaced with this, say, resistor over here, it's an integrator. Option B would have been correct. Option C is just, I think, negative sign. It doesn't make sense. Option D, of course, is the right answer. Question number 29. During a non-invasive measurement of blood pressure, mean arterial pressure was observed to be 100 mmHg. If systolic pressure is 150 mmHg, the diastolic pressure would be. Okay, so we are given the mean arterial pressure 100 mmHg. It's mean, so it's average of systolic pressure and diastolic pressure. And systolic pressure is given to be 150 mmHg, right? So it's 150. This implies diastolic pressure that we want is 200 minus 150, which is 50 mmHg, right? And that corresponds to option D, which is wrong. Okay, the correct answer is option B, which is 75 mmHg. Okay, so mean arterial pressure is not just the average of diastole and systole. Let's look at why that's the case. So I have shown a pressure waveform here. Okay, wherever the pressure rises is where the heart pumps. It's not the systole. Wherever the pressure drops, that's where the heart fills. It's called the diastole. Okay, so the systolic pressure is somewhere over here. Okay, and diastolic pressure is somewhere over here. Okay, and the mean pressure, mean of this waveform is the mean arterial pressure. That mean, or P bar, is given by average of this waveform, P of t dt, 0 to t, along this total heartbeat time, which is capital T. Okay. Now, based on the information that is given, what we know is that the systole is usually 1/3 of the total heartbeat. So systole makes 1/3 of the cycle, diastole makes 2/3 of the cycle. Okay, so the correct expression for the average here is 1/3 of systole by and 2/3 of diastole. Okay, this is a very good approximation for this integral over here. Based on that, let's go back and calculate what PD is. If you do that, your PD will turn out to be 75 mmHg. Question number 30. Two loads are connected to AC supply mains as depicted in the figure. One load draws 10 kilowatts, whereas the other load of 10 kilovolt ampere is operated at 0.6 power factor lagging. To achieve an overall power factor of 0.9544 lagging, the nearest kVAR rating of the capacitor bank needed to be connected across the supply mains is equal to. Okay, so essentially we have a AC supply, there are two loads. Okay, let me explain what this is in a moment, but we want to add another capacitor to this so that we end up with the overall power factor of this being 0.9544. Okay, in AC circuits the voltage is not in phase with the current, right? So just the product of voltage and current, that's known as the apparent power. Okay, but if you look at the component of that power that is in phase, where the voltage and current are in phase, VI cos phi, right? That's called the active or real or true power. Okay, and the component that's not in phase, where the voltage and current is not in phase, that's called the reactive power. Units for this is volt ampere, watts, and volt ampere reactive. Okay, and the power factor here is essentially the ratio of true power by apparent power. That's a power factor. Okay, so for given any loads, it's a good idea to just draw the power triangle. The nice thing is you can add and subtract sides because they satisfy complex arithmetic. Okay, for example, so let me explain what I mean by that. So 10 kilowatts, so the power triangle corresponding to this load 1, is just a single line, because all of it is active power. There is no reactive component. Okay, that's also equal to the apparent power. So this is a triangle with zero height. This thing, so 10 kilovolt ampere is the apparent power. Okay, power factor lagging means this triangle is facing upward, leading means triangle is facing downward. So power factor is 0.6, so ratio of this by this is 0.6, so this is 6. Okay, so this is 6, this is 6, this is a right triangle, so this should be 8. Okay, now they satisfy, you can add and subtract size, base and height. So if you add these two, the net triangle for this is 10 plus 6, which is 16, that's the base of this. The height of this is 8. What we want is, we want to end up, so this is where we are currently, the black triangle. We want to end up at a red triangle whose power factor is 0.99. Okay, so 16 divided by 0.95. Okay, that should be the length of this. That's the definition of power factor. So that turns out to be 16.76. Corresponding to that, the height over here is 5 kVAR. Okay, if 8 has to become 5, we need to add a capacitor that has a leading downward triangle. This is a triangle with just no base, just the height. Okay, we need to add a triangle of, we need to bring it down by 3 kVAR. So this is the effect of the capacitor. There is no active true power in a capacitor, just all of it is reactive power. The value we want is 3, because that will bring 8 down to 5. So the answer here is option A, which is 3. 31st question. The nearest value of power dissipated in the 3 ohm resistance in the circuit is. So we are given a circuit, we have 3 ohm resistance, we need to find the power dissipated in it. I'm going to solve it in a straightforward approach. Okay, if you know the current flowing through the resistance, we can find the power dissipated in it. In order to find the current, I am just going to use Kirchhoff's first law and second law. Okay, so let's say we have a potential X over here, and let's say this is grounded, so this potential is 0. I'm going to say this is I1, and because this is 2A, this is going to be I1 minus 2, and this is going to be I1 minus 2. Let me say this is I2 and this is I3. Okay, first thing, so we have a 2 and 2 in series, so let's make this equivalent. So this is 2 plus 2, which is 4. Okay, now we have summation of currents in this node. So I2 is the sum of I1 minus 2 and I3. Okay, so that is I1 minus 2 plus I3. Okay, now let's write down what I1 and I3 are in terms of X. So this will be I1 is X by 3 minus 2 plus I3 is X by 4. This implies I2 is 7X by 12 minus 2, right? And then let's write down the potential rise here in this edge is 0 to X, right? X. So 0, then there is an increase of plus 2, then there is a drop of current flows in this way, there is a drop of minus 4, right? Okay, so minus 4 I2, that is, we know to be X. Now plug in for I2 over here and solve for X, just one variable, linear equation, we get X is 3. Okay, once we know X is 3, we know I1 is X by 3, which is 1 amps, right? So this implies the power dissipated as P is VI. In terms of current, it's I1 square R. So this is 1 square into 3, that is 3. Correct answer is option A, which is 3 watts.
32nd question. A second order low pass filter is being constructed by cascading two first order low pass filters with the following transfer functions. H1 of j omega is 1 by 1 plus j omega by omega 1. H2 of j omega is 1 by 1 plus j omega by omega 2, where omega and omega 2 are the respective 3 dB cutoff frequencies. The undamped natural frequency WC of the resulting second order low pass filter is. Okay, so we are given two transfer functions for first order systems. They are being cascaded. We want the natural frequency of the cascaded system, right? So this is a very simple problem. In order to find the natural frequency, all we need to do is to write the transfer function for the cascaded system in the standard form. So the standard form for a second order system is given over here. So it's s over omega n square plus 2 zeta by omega n s plus 1, okay? And omega n is the natural frequency and zeta is what is known as the damping factor. What I am going to do is, first thing, we are looking at undamped natural frequencies, right? So now we can substitute j omega to be yes, the frequency domain. We can convert by the transfer functions in the frequency domain, and so that's the first step. This is to just compare with the standard form, okay? So h1 of s is s by omega 1, h2 of s is, okay, so we have this. And now what is the transfer function for the cascaded system? Is it h1 of s plus h2 of s? No, it's h1 of s multiplied by h2 of s, okay? So that would turn out to be 1 by, multiply these two terms in the denominator, we get this expression, okay? Now we can compare this term by term to the standard form, and we have omega n squared is omega 1 omega 2. That implies omega n, the natural frequency is root of omega 1 omega 2, okay? That corresponds to option A. Omega n here is omega c in the problem. Question number 33. Match the bridge type with the application given below. Okay, 4 bridges are given and 4 applications are given. The right answer is PL, QK, RN, SM. That's option A. And I have written the bridges and the corresponding applications so that they actually match. Okay, so this is just a memory based question. Just know what is what. And of course, we have 2 inductance measurement bridges. That's the Maxwell and Hay. Okay, Maxwell is used for medium inductance and Hay is used for high inductance. Then Kelvin is used for resistance, and then capacitance is sharing bridge. There is one more capacitance measurement bridge, that's Vane, okay, but didn't show up in this question. 34th question. For a non-unity feedback system at G of s is 12 by s plus 2 and H of s is 2 by s plus 3, the magnitude of steady state error to a unit step input is. The given system is non-unity feedback, right? So if you convert it into unity feedback, G1 of s will be G of s by 1 plus G of s into H of s minus 1, which is what is written over here. So convert the non-unity feedback system into a unity feedback system, and once you have G1 of s, error is defined as this. Then steady state error ESS is given by limit t tends to 0, t tends to infinity, E of t, error of t, and by finite value theorem this becomes limit s tends to 0, s times E of s, okay? And because it's step input, unit step input, okay, so this means R of s is 1 by s, okay? So we have ESS is limit s tends to 0, s 1 by s by 1 plus G1 of s, right? So all we need to do is to find limit s tends to 0 and plug that in here, okay? Let's call that k, that is limit s tends to 0, G1 of s is k, okay? That is, you can get
G1 of S to be 12 times S plus 3 by S plus 3 into S plus 2 plus 12 times minus S minus 1. When you plug S tends to 0, so this goes to 0, 0, 0 and 0. So this term becomes 12 times 3 by 2 into 3 minus 12. Okay, so this becomes minus 6. So plug that value over here, and to get the magnitude of the error, it's the magnitude of this. Okay, so limit S tends to 0, G1 of S is minus 6. So let's plug that in here. Minus 6, that becomes 1 by 5, which is 0.2. This corresponds to option D. Okay, this is an important problem from the control system because there is a lot of confusion and controversy over what the correct answer is and what the correct method is. But IITs always say this is the way to do it and this is the correct answer. 35th question. Match the Boolean expression with its minimal realization. 4 Boolean expressions are given, 4 minimal realizations are given. We need to match them. The straightforward way to do this is to use the Boolean operations, standard Boolean identities. The AND identities are given here and the OR identities are given here. For example, A and not A is 0. Then there are a couple from the De Morgan's law. Okay, so not of A or B is not A and not B. The most important one over here is called the adsorption law. So A or not A B is A or B. Okay, this is one of the most important laws and its corollary also is written over here. So I will show examples for two Boolean expressions on how to minimize them. Okay, so we have the Boolean expression P over here. So once we have something like this, look for a combination where at least two of those terms repeat. Okay, for example, X bar and Z bar is in this term, X bar and Z bar in this term. They commute, so we can write this as X bar Z bar times what is left is Y bar plus Y, right, plus X bar Y Z. Because they commute, I could write it this way and take the X bar Z bar outside. And what is Y bar or Y? Y bar or Y is, we know it's 1, right? Okay, so this is 1. So if it is 1, anything and 1 is always that anything, so it's X bar Z bar. Okay, now let's take X common from here. So this becomes X bar Z bar plus Y Z. Okay, can you recognize how to minimize this further from the adsorption law? Okay, yeah, just use the corollary. Okay, so this becomes X bar Z bar plus Y. Okay, so P corresponds to the minimal realization X bar Z bar plus Y, and that is option L. Okay, let me do it for one more thing. So we have X Y Z. So let me take X Z is common in both. So X Z times Y plus Y bar plus X Y Z bar. Okay, Y plus Y bar becomes 1. And then we have, let me take X common, Z plus Y Z bar. Okay, Z plus Y Z bar from the adsorption law is Z plus Y. So this corresponds to minimal realization X times Z plus Y, and that is option K. So PL and QK, with this I think we can pick the right answer, which is option B. 36th question. The glomerular filtration process of kidney is modeled as a flat membrane with pores of radius 1 nanometer and length of pore 60 nanometer. The viscosity of the fluid is 0.002 Pascal second. The aggregate area of the pores make up 5% of the total surface area of the membrane. The average pressure on the blood side of the membrane is 8000 Pascal and on the ultrafiltrate side is 6200 Pascal. The total available area of membrane is 1.5 meter square. the nearest value of resulting filtration rate in centimeter cube per minute is. Okay, the question reads lengthy, but solution is very simple. If you have seen my video on the analogy between electrical circuits and fluid flow systems, okay, you know the flow in a tube is given by the pressure gradient delta P, right, pressure head, times pi r power 4, where r is the radius of the tube, by 8 mu L. Mu is the viscosity and L is the length of the tube. Okay, so this is the amount of flow if we were given just one pore, right? But instead of one pore, we are given many pores. How many such pores are there? Okay, number of pores in the membrane will be given by, right, the area of the pores by area of one pore. So that will give the total number of pores. So that times flow in one pore would be the total flow, right? So area by area of one pore, which is pi r squared. Okay, so now just plug in all the values over here and we'll get the total flow. And to make things more apparent, okay, so we got pi and this becomes r power 2. Area is 5% of 1.5 meter square. So this is 1.5 times 5 by 100, right? And the pressure head, that is 8000 minus 6200, right? That is delta P. Now r square is 1 into 10 power minus 9 square, right? We have 8, mu is given to be 0.002 Pascal second, and length is 60 into 10 power minus 9. Okay, so this value turns out to be approximately 1.4 into 10 power minus 7 meter per second, so meter cube per second, and this times 10 power 6 into 60 will get centimeter cube per minute, and that value turns out to be 8.4 centimeter cube per minute, and the correct answer is option C. Very simple problem. All you need to know is, so what is the flow in one of the pores, and then multiply that by the number of pores, which you need to infer from the problem. 37th question. During the resting state, the voltage outside the cell membrane compared to that inside the cell membrane is dash. Under such condition, the intracellular and extracellular regions have dash and dash concentrations respectively. Okay, so we are looking at, first of all, the resting state, right? So under resting state, say we have a cell membrane on the intracellular side in this side, and the extracellular side on that side. Okay, usually there are more potassium ions inside the cell, about 140 milliequivalents per ml, and outside the cell it's just 4. The sodium ions, on the other hand, it's just 10 milliequivalents per ml inside the cell. Outside the cell it's close to 142 milliequivalents per ml, and because of this, and overall inside the cells there are more negative ions, okay, compared to the outside the cell. So inside the cell the potential is close to minus 70 millivolts. Outside the cell it's close to 0. Okay, so this difference is what you get as the membrane potential, right? The resting membrane potential is close to minus 70. Okay, now having said this, now we need to compare the potential outside and the intracellular sodium and potassium and the extracellular sodium potassium. Okay, first thing, so the potential outside is going to be more positive, right? So inside it's negative, it's close to minus 70. So either this or this. And as far as the intracellular goes, intracellular, the potentium is higher. So these two options are okay. And extracellular, the sodium is always higher. So this and perhaps this. So the only option that satisfies all three is option A. So the correct answer is option A. This is one of the fundamental problems in, fundamental facts, ideas in physiology, things about membrane potential. It's a good idea to know that. 38th question. I think this is one of the most ill-posed questions in the whole question paper. The tensile strength of a degradable suture used for a surgical procedure in the human body is observed to decrease exponentially from its original strength by 40% and 50% after 10 days and 20 days respectively. The closest approximation of the time taken for the tensile strength to decay to 20% of its original value would be dash. Okay. The reason this is ill-posed is, okay, they ask you to fit an exponential function given just 2 points, right? So let's try to visualize the information given in the figure. Let's say this is a tensile strength and this is the time in days, okay? So initially it's like 100%, then after 10 days its value drops by 40%. So its current value is 60, okay? Drop is 40, so its value is 60. Then after 20 days, value drops by 50%, so its current value is 50%. Now the question asks you, when will its value decay to 20%? So in which day would this value be like 20%? So a couple of oddities show up here. First of all, if you try to fit a function y is 100 power e power bt, couple of things. So you do not know whether this function is going to be exponential here or here, or even if the rate of exponential drop is going to be the same here compared to this one. For example, it took 20 days for it to drop by 50%, right? So in the 10 days I would have expected it to be close to 75%, right? Or if the exponential drop had been like this one, then again the 60% and 50% do not match well. After if the drop is 60% in 10 days, I would have expected a much steeper drop in 20 days. So the best curve that makes sense here is y is, let's start from this day when they say it's going to drop exponentially. So on that day it's 60. If you write it as e power delta t, okay, so at this day delta t is 0, so e power 0 is 1 and we get y's value to be 60. So let's start with this function and try to find the value of b, and then subsequently find the time at which it will become 20%. So okay, when is y 50? Y is 50 when e power b times delta t is 10 to 20, it's 20 minus 10, which is 10, right? Now try to solve for b by taking ln on both sides. We get b's value to be minus 0.01823. Okay, so once we know the value of b, we want y is going to be 20 of 60 e power b times delta t. Again, take ln on both sides and find the value of delta t. We get delta t to be 60.36. Note that at this point we know what b value is. Okay, so delta t from the 10th day is 60.36. So when will the value actually decay to 20%? It's t, that's 10 initially plus delta t, right? So the answer that we are looking for is equal to 10 plus delta t, which is 70.36. This is closest to 70 in option D, which is supposed to be the correct answer. Okay, this problem I think is ill-posed, but this is the best solution that I have. 39th question. 60 kg person is standing on one foot on a force plate. The ground reaction force is found to act 40 mm anterior to the ankle joint. The mass center of a foot is 60 mm from the trochanter knee ankle line. The weight of the foot is 0.8 kg. The closest value of magnitude of moment acting on the ankle joint is. Okay, so we are given the weight of the person, he is standing on one foot, and also the weight of the foot is given. Now we want to find the moment acting at the ankle joint. All we need to do is to draw the free body diagram of the ankle and write the summation of moments. Okay, so I have drawn the idealized version of the ankle over here. So we have the ground reaction for 60 kg, weight of the foot that's 0.8 kg acting at 40 and 80 mm. Okay, and because we make a cut here in order to draw the free body diagram, there will be reaction forces Rx, Ry and M. Our task is to find M, which we can easily do by finding or writing the moment equilibrium equation. Sum of moments, all the moments is 0, and let's make the clockwise direction to be positive. Okay, so the unknown moment acts in the clockwise direction plus the moment due to the foot, it's 0.8 times the distance at which it acts, 8 into 10 power minus 3. Is that correct? No, this is in weight. We need to convert it into newtons, so there will be a 9.8 factor, okay? And then the reaction force is acting in the anti-clockwise direction, so it's minus 9. 60 into 40 into 10 power minus 3, it's momentum, times, of course, to convert it into force, you multiply by acceleration due to gravity, 9.8, okay? And this should be 0 because of moment equilibrium, and this implies the moment is 23 Newton meter, which is option A. Question 40. Temperature of bone cement is increased from 37 to 87 degrees during femoral hip orthoplasty. Cement thickness is noted to be 20 mm. Stress developed due to exothermic reaction of bone cement during the polymerization process and shrinkage of the bone cement respectively are. Assume some conditions, okay, and coefficient of thermal expansion and Young's modulus are given. All it says is, okay, what is the thermal strain, and then if you don't allow the material to expand, put it in between the bone and the implant, don't allow it to expand, okay, what is the stress developed? That's the thing. And of course, from the description now, it should be obvious that we are talking about a thermal elastic material. So thermal strain is given by alpha times delta T, okay. So it depends on, the strain in the material depends on the change in temperature. So change in temperature is 87 minus 37, okay, and alpha is given to be 90 into 10 power minus 6. Based on this, we can find the thermal strain, and the change in length is length times strain, okay, and length is given to be 20 mm, and change in length we get it to be 90 micrometers. And now this is the amount of change in length if the bone cement is free to expand, but it's in between the implant and the bone, so it's not free to expand, okay. So the strain in the bone cement will be 0, but that will develop a stress, and that could be quantified using, the stress would be Young's modulus time strain minus epsilon T, okay, because it is not allowed to expand in between the two cylinders. Epsilon is 0, and we know what is E. E is 3.5 into 10 power minus 9 pascals. This implies sigma is 15.75 MPa. So these two corresponds to option A. For the first question, this is one of the most important questions from the whole GATE paper, and the question is also framed very interestingly. A patient is initially imaged in a 1 Tesla MRI scanner and induced voltage is found to be equal to V1. Expression for the magnitude of the received coil voltage R of coil is given below, okay. And when the patient is shifted to a 3 Tesla MRI scanner that uses the same R of coil and the slice thickness is half, the magnitude of the induced voltage was found to be equal to V2, ratio of V2 and V1. So in this question, they almost like they give you the answer, it looks as if they give you the answer, but that's not the case. The actual answer is hidden in all this surface level expression that they have given. So they are saying they are using two MRI machines, one with 1 Tesla and another one with 3 Tesla, and they want the ratio of the induced voltage in the R of coil, right? And induced voltage magnitude of that is given by this. Okay, so let's look at how each of these terms get affected because of varying the 1 Tesla machine to a 3 Tesla machine. Okay, so we know the Larmor frequency that depends on the amount of external magnetic field. So this depends on the whether it's 1 Tesla or 3 Tesla. Then they say the slice volume is half, right? So we okay, it's proportional to the slice volume as such, this term. Then m naught is the net magnetic moment in the longitudinal direction. It turns out that is also proportional to P naught. It depends on the Boltzmann constant, temperature and all that, but for this problem it is proportional to B naught. That's the power of the MRI machine, okay. And alpha is the flip angle, right? The flip angle, It's actually again it's proportional to B1, the transverse magnetic field. That's from the RF pulse. So it's not directly related to B0, the main magnetic field applied in the machine. So this shouldn't show up. And finally, beta R is known as the magnetic field sensitivity of the received coil. This depends on things like patient's impedance, the proximity of the RF sensor, and the type of RF sensor, whether it's surface coil or body coil and all that. So overall, we have three terms that affect this ratio. Okay, so in this case, this is equal to, there is a B0 term from gamma naught, then okay, BS2, and there is a B0 term from M0. So it's B0 square by BS2. So B0 2, 2, B0 1, BS1, B0 1. Okay, so B0, the ratio of B0 2 over B0 1 is 3. So it's 3 square, and the slice volume is halved. So ratio of BS2 by BS1 is 1 by 2. So that gives 4.5, which is option C. Yeah, this is a very important question, and based on how hidden the answer is, I think the preparation for MRI based topics demands a very high level of preparation to attend and to answer all these questions. 42nd question. Another simple question from ultrasound. 3 MHz ultrasound transducer transmits a 3 cycle long pulse into a soft tissue at normal incidence to fat and liver interface. The axial resolution and the amplitude reflection coefficient at fat liver interface respectively are speed of ultrasound in tissue, fat and liver are given, then density of fat and liver also given. Okay, first thing, the answer, the axial resolution, okay, of ultrasound is given by number of pulses time wavelength of the ultrasound by 2. Okay, we know the number of pulses is 3 cycles per second, right? And the lambda is not directly given, but instead the frequency is given. So just convert this into C over F, okay, where C is the speed of ultrasound and tissue. I think it's given as 1500 meters per second, and this is given to be 3 megahertz, right? So 3 into 10 power 6 hertz. So this gives 0.75 into 10 power minus 3 meters, which corresponds to 0.75 mm. Okay, the amplitude of reflection coefficient, okay, when the incidence is normal, right, then the expression is pretty simple. It's just Z2 minus Z1 by Z2 plus Z1, where Z2 and Z1 are impedances in the different tissues, especially impedances in fat and liver. Okay, impedance in one particular tissue is given by Z is its density times the velocity of the ultrasound, so rho C. Okay, for example, Z fat is given by rho fat times C fat. Okay, so just find Z fat and then Z liver and find this ratio. So Z1 is say Z fat and Z2 is Z liver, and find this particular ratio. We'll get that to be 0.11. Again, the number of formulas in ultrasound, they are very, very limited, so it's a good idea to remember them. 43rd question. The forward bias current of a silicon diode is being calculated from the exponential model of the VI characteristics. The diode current ID is 1 milliamps at a voltage drop, VD is 0.7 volts. Nearest value of ID when VD is 0.8 volts. Assume thermal voltage to be 25.3 millivolts for silicon diode. Okay, so they have given they said the voltage current characteristics for a thermal diode, right? For a diode is in forward bias is exponential. So the current in it depends on a constant Is times exponential of the forward bias voltage by thermal voltage, okay, minus 1. And they have said what the current is at 0.7 volt, right? They want the current at 0.8 volt. So just use this relation and find the current in this particular thing, okay? And while doing that, it would help to make an approximation here, which is this term is usually very big compared to 1. So we can neglect minus 1. So let me do that. So we have like I1 is Is times e power 0.7 by Vt, right? And we have I1 as 1 milliamps, so 1 into 10 power minus 3, and Vt is, we have to be 25.3 millivolts, right? So now I2 is Is power e power 0.8 by Vt, right? So notice I have neglected the 1 because usually that term is very, very small compared to this e power term. Okay, so this is approximate, and I2 is I1 e power 0.8 by Vt, just divided by this expression, right? And you get minus 0.7 by Vt. Now this is known, Vt is known, just plug in the values and find I2. That turns out to be 54 into 10 power minus 3 amps. That is closest to option C, which is 52 milliamps. 44th question. The continuous random variable x has a probability density function given by f of x is e power minus alpha mod x from minus infinity to x infinity, where alpha is a real constant. The variance of x is dash, correct up to 1 decimal place. Okay, so we are given a probability distribution function. First thing to notice is that it's symmetrical about the y-axis, right? So, and it drops exponentially from both the sides. Okay, a straightforward approach to do this is to first find what this constant is. So it's a PDF, so integral minus infinity to infinity f of x dx is 1. So if you do this integral, you will get the constant to be 2. Then notice this distribution is symmetric, right? Because of that, the mean of this is essentially 0. X is 0 is the mean. Okay, you can directly write down the mean to be 0. Third thing, once you know the mean, you can calculate the variance, sigma square, which is the variance. That is minus infinity to infinity, x minus mu square f of x dx. You know mu is 0, so calculate this integral using integration of parts twice or thrice, and you can find that value to be 0.5. But we don't have time to do all this, especially this integration by parts in a GATE exam. Okay, so the shortest way to answer this question is to recognize that this is a Laplace distribution, which is, okay, 1 by 2b exponential of minus x minus mu by b. Okay, with b is, so this coefficient, this term is 1 in this function, right? Which means b is 1 over 2, first thing, and we know mu is 0. Again, x minus 0, observed value of that. Once you realize this, b is 1 over 2, the variance of a Laplace distribution is 2b square, which is 2 times 1 by 4, which is 0.5. This is the shortest way to answer this question. It involves a bit of memory, but Laplace distribution is one of the standard distributions, and it's a good idea to remember what the distribution is, what its variance and mean are. 45th question. The magnitude of the gradient of the function f of x comma y equals x square plus y square at the point 1 comma 1 s dash, rounded off to 2 decimal places. So we are given f of x is x square plus y square. We know gradient of f is dou f by dou x in the I direction plus dou f by dou y in the j direction. Magnitude of this is just square root of dou f by dou x whole square, the first term square, plus dou f by dou y, the second term square. Okay, just find dou f by dou x, dou f by dou y, and calculate this root at 1 comma 1. We are done. Okay, so dou f by dou x is 2x, dou f by dou y is 2y, and gradient of f is square root of dou f by dou x square, so 2x square plus 2y square. Okay, and we want to estimate this at 1 comma 1, right?
So this turns out to be root of 2 times 1 is 2. So 2 square is 4 plus 2 times 1 is 2. 2 square is 4. So this is root 8, that is 2.83, which is the answer for this question. 46th question. The value of the following double integral is dash, where R is the first quadrant of the circle with center at the origin and radius of 1 unit. Okay, so we need to integrate this function in this area which is the first quadrant of a circle with radius 1. Okay, and all we need to do is find what integral of xy is in the first quadrant. Okay, so this I'm going to integrate it along the y direction first, then along the x direction. So the first integral is 0 to 1, x varies from 0 to 1 of that, and y varies from 0. What is the bottom limit of y? This function is root of 1 minus x square, right? So square root of 1 minus x square, xy. I integrate it with y first, then I integrate it with x. Okay, so this term is 0 to 1, x doesn't matter, and its integral of y is y square by 0 to root of 1 minus x square. Okay, so this becomes, substitute this limit, root of 1 minus x square, okay, dx, and this becomes, so now this is just take the half outside of this, and x times x cube, right? So half of integral of x is x square by 2, integral of x cube is x power 4 by 4 from the limit 0 to 1, and this is half of 1 by 2 minus 1 by 4, which is half of 1 by 4, which is 1 by 8, which is 0.125. Question number 47. A gynecologist recorded the blood pressure of patients as shown in the table below. Using regression process, diastolic BP of a 38-year-old patient, mmHg is dash. Okay, so we have age here and we have blood pressure here. We are given some data points and we want to find the blood pressure of a patient who is 38 years old. Okay, so 38 years old is somewhere over here. So okay, this problem is going to take time. Okay, I will do it at the end of the exam, but this is a very easy problem, so I will also practice a lot during preparation. But if I don't have time, I'm just going to take a blind guess. So 38 is somewhere over here. Okay, and this would be my crude line fit, a regression fit to it, and based on that my guess would be some number between 85 and 90. So let me show the proper way to solve this, and let's see if you had to pick a number randomly between this, let's see how good it is. Another thing, as I said, this is not a multiple choice question, right? It's a fill in the blank type question, so fill it up. I would fill it up with one of these numbers. Okay, so for regression, linear regression, we need to fit a function y is a plus bx. Okay, the coefficient a and b given some data points xi and yi, say the pp and the age, right? So that depends on sum of this product and sum of the square terms. Okay, simple way to do that is, okay, we have xi's, yi's. Xi bar is average of this, it's 29. Yi bar is average of this is 72. Find xi minus xi bar, so 23 minus 29 minus 6, fill this one up. Find yi minus y bar. Okay, so 65 minus 72, that's minus 7. 60 minus 72 minus 12, fill this up. Okay, and then product of these two, so minus 6 into minus 7, 42. Similarly, all fill this table, and this table square of xi minus xi bar, so 6 square is 36, 5 square is 25. Again fill this up. So the top
sum in the numerator here is 421 and sum in the denominator is 248. Okay, so using these two, I get B hat is 1.7, A hat is 22.7, and then I can find Y for a new age, which is 38. I get that to be 87.3, at least within the range that I just guessed initially. So the right value for this is between 86.5 and 87.7.
48th question. Your person in standing position first flexes the hip by 50 degrees from the initial trochanter knee ankle line and then flexes knee by 20 degrees. Distance of ankle joint from the initial trochanter knee ankle line is dash, rounded off to nearest integer. Distance between hip joint and knee joint is 400 millimeters. Distance between knee joint and ankle joint is 300 millimeters. Okay, first let's look at what the question means by flexes the hip by 50 degrees and flexes the knee by 20 degrees. This is the trochanter knee line, flexes hip by 50 degrees, right? And then flexes knee by 20 degrees. This is incorrect. Flexes hip by 50 degrees and then flexes knee by 20 degrees. Again, a very simple problem. Okay, so a person is initially standing, is a trochanter knee ankle line. Okay, from that his distance between hip and knee is 400 mm, distance between knee and ankle is 300 mm. Okay, so from this initial line he flexes the hip by 50 degrees. Okay, so the knee is at this position. If he hadn't flexed the knee, it would have been a straight line, but he also flexes the knee by 20 degrees. Okay, so the angle that the knee makes with the vertical is 50 minus 20, which is 30 degrees. Question asks, what is the distance of the ankle joint from this initial trochanter knee line? What is this total distance? This total distance is this distance, which is 400 sine 50 degree, okay, plus this distance. This is 300 this length times sine of 30 degrees. Okay, this comes out to be 456.4. So the nearest integer, I suppose, is 456. 49th question. A chest radiograph of 36 cm by 48 cm is digitized. If you want to preserve details in the image to a spatial resolution of 6 cycles per mm, the approximate image data size in megabytes for an 8-bit quantization is dash, rounded off to 2 decimal places. Okay, so the key detail in this question is we need to understand what is cycles per mm. We need to understand this unit for the resolution. Okay, so let's take a single point source. Okay, so if this is a single point source, the way its projection will appear in the image will be a slight spread of the point source. Okay, a single peak will be slightly spread on either side. Okay, so similarly, if there are 2 point sources, okay, one here and one here, we'll have 2 peaks like this. Okay, so essentially, okay, this is a single point source is known as a line. Okay, 2 lines are known as what is known as a line pair. Okay, distance between peak of 2 lines, 2 consecutive lines, okay, is known as a cycle. It involves a peak, which is a bright spot, a dark spot, and a bright spot. Okay, so from here to here is known as what is a cycle. So this resolution could be instead given in, say, number of lines per mm or number of line pairs per mm. Okay, so 6 cycles per mm is 6 line pairs per mm and or 12 lines per mm. Okay, so given this, if we somehow relate it to the number of pixels that are needed for this resolution, we can go ahead and find the data size, okay, based on this size of the radiograph. How do you find the number of pixels? Okay, so I'm going to make this very informal. For this peak, we need 1 pixel, right? And for
this dot spot, we need another pixel. And again, for this pixel, for this peak, we need another pixel. If you notice, this essentially means for one cycle, we need 2 pixels, right? Because this pixel is being shared by this dot spot as well. So one cycle needs 2 pixels, 1 full pixel and half of this. Okay, very, very informally. So this is what is known as the Nyquist frequency. If the pixels are bigger than this, we cannot distinguish these point sources, and this essentially is 0.5 cycles per pixel. Okay, so from this, the way we can find the number of pixels is essentially 6 by 0.5, which is 12 pixels per mm. Based on the Nyquist frequency, essentially if we need 6 cycles per mm, we need 12 pixels per mm. Okay, with that, then the answer is pretty straightforward. Okay, so because this is in mm, I'm going to convert everything in mm. So 36 centimeters 360. Along the length, we need 12 pixels per mm. So along 360 mm, we need 360 into 12. That times again 480. That is the height. Okay, that times 12. So we need this many number of pixels. Okay, and how many bytes corresponds to these pixels? Okay, it's a 8-bit quantization, so it's times 8 bits. Okay, but ultimately we want things in bytes, so 8 by 8. Okay, number of bytes, and we want the answer in megabytes. So divide this by 1024, we get kilobytes. Divided by 1024, again we get megabytes. Okay, so this factor over here turns out to be 23.73 megabytes. A very, very simple question. All we need to know is how to convert this resolution into the number of pixels per mm. Okay, again, instead of 6 cycles per mm, instead they could give 6 lines per mm, or say 12 lines per mm, or 6 line pairs per mm. 50th question. An X-ray radiography scenario is shown in the figure. The number of incident photons Na is equal to 2 into 10 power 6 at 50 electron volt. Number of photons Nd that exit the tissue is dash into 10 power 6. Use linear attenuation coefficient for soft tissue and blood as 0.4 and 0.2 per centimeter respectively. Okay, so we have some piece of tissue. A number of photons enter here and a number of photons exit here, right? Linear attenuation coefficient by definition is, so intensity of light entering, that times e power attenuation coefficient times the distance of the tissue. Okay, that will be the intensity of light that exits. But here we don't have a constant attenuation coefficient throughout, we have a non-homogeneous medium. So this term over here becomes an integral, right? E power minus x into x out, okay, mu of x dx. Okay, so in order to find the number of photons that exit, take the number of photons that go into the system, multiply that by e power this integral over here, and that's very, very simple. Okay, we have 2 into 10 power 6 times e power minus of mu of x is constant across length, right? So 2 times 0.4 for the first part, okay, plus 0.5 times 0.2 plus 1 times 0.4. Okay, so just find this e power, this whole term, you will get the answer, and we need the answer in terms of 10 power 6, so find 2 times this fraction, which will be 0.55. 51st question. The wavelength of an electron accelerated to a potential of 1 volt is dash nanometers. Mass of electron, Planck's constant, and charge of electron is given. Okay, so wavelength of an accelerated electron, so the de Broglie wavelength is given by h over p, where h is Planck's constant and p is the momentum of the electron. I think we can find the momentum of the electron using energy conservation. So the work done on the electron when it's being accelerated is q times v. That should be equal to the change in kinetic energy, half mv square, right? So from this, let's try to calculate the momentum. You know, P square is m square v square, right? mv square. So that is 2 times mqv. So this equation implies this. Okay. From this we know P is root of this term, and we have h to be h by root of 2mqv. Okay, so in the question we know h is given, m is given, q is given, and b equals 1. From that we can calculate this term, the wavelength, which turns out to be 1.3 into 10 power minus 9 meters, which is 1.23 nanometers. 52nd question. In a permanent magnet moving coil instrument having following specifications, the angular deflection of the pointer for a coil current of 100 microamps will be dash degrees. Magnetic flux density, torsional spring constant, cross-sectional area of the coil, number of turns of the coil are given. Okay, so the degree, right, the angular deflection theta, that would be equal to the torque in the coil by the spring constant K, right? The torque in the coil, PMMC coil, is given by NBIA, where N is the number of turns in the coil, B is the flux density, magnetic flux density, I is the current, and A is the area. Okay, so TD is NBIA, and from this we can directly find what the degree is. So N here is 500, B is 1.5 Tesla, we can leave it as such. I is 100 microamps, so 100 into 10 power minus 6. Area is 2.5 centimeter square, so it's 2.5 into 10 power minus 4 meter square, and K is 2 into 10 power minus 6 Newton meter per degree. Find this, just calculate this expression, that turns out to be 9.375 degrees, which is the answer. 53rd question. Arterial blood extracted from a healthy adult showed an oxygen partial pressure value of 40 mmHg. Total oxygen content in the arterial blood measured in percentage volume by volume as dash. Solubility of oxygen in blood is given. Hemoglobin oxygen saturation, oxygen carrying capacity of hemoglobin, and arterial blood hemoglobin concentrations are also given. Okay, so total oxygen concentration in the blood is given by the amount of oxygen that is bound in the hemoglobin, right? So that is oxygen carrying capacity of one hemoglobin, right? That's in ml per gram. That times the hemoglobin saturation, that is 95%, so 95 by 100, that times arterial hemoglobin concentration, right? 15 gram per dl. Okay, this turns out to be 19.095, and this answer is incorrect. Okay, because the total oxygen content in the blood is the amount of oxygen that's bound to the hemoglobin plus, okay, the amount of oxygen that is dissolved in the blood, which is usually a small component, but for this problem even that also matters. Okay, so solubility of oxygen in this blood is, which this term equals 0.003 per mmHg. We have like partial pressure of oxygen as 40 mmHg. So this times 40, okay, will be the amount of oxygen that is dissolved in the blood, and this is in ml per dl, and this is in ml per dl. The total is the sum of this term and this term. So add 19.095 plus this term, which is 0.12, that turns out to be 19.215. 54th question. In the process of measuring blood flow from an artery using zinc clamp magnetic flow probe, voltage recorded across diametrically opposite sides of the artery is 3.75 nanovolt. The blood flow rate through the artery is dash centimeter cube per second. Inner diameter of the C clamp is 0.5 centimeter and magnetic flux density is 1.5 into 10 power minus 5 Weber per meter square. Okay, so we have a magnetic flow probe, right? The potential developed in the magnetic flow probe is given by BLB, where B is the magnetic flux density, L is the diameter of the C clamp, and V is the velocity of blood flow. Okay, we want blood flow rate, so let's convert this velocity in terms of flow. So V is nothing but flow over area, right? And the area is, for a C clamp, it's pi r square, or it's pi diameter L by 2 square, right? Now from this we know B is 1.5 into 10 power minus 5. Okay, the potential developed is 3.75 into 10 power minus 9 volt, and L, which is the diameter of the clamp, which is 0.5 into 10 power minus 2 meters, and we know L, we can find what Q was. Okay, try to find Q from this expression. The value that I get is 0.981 centimeter cube per second. You will get it in meter cube per second. Convert that into centimeter cube per second. Last question, that is question number 55. A cell is injected with a current I of t is U of t to produce a change in the intracellular membrane voltage V of t. The cell membrane is modeled as a linear system with impulse response H of t is A e power minus t by tau U of t. The cell membrane voltage output at 5 milliseconds is dash millivolts. Constants A and tau are given. I am going to call tau as tau naught. Okay, essentially what this says is the voltage is like the output of the system, the current is like the input of the system. The current is a step function U of t. Okay, and the impulse response of the system is given. Instead of a step response, if you had a unit impulse, its response is essentially exponentially decaying function. Okay, now V of t we can find using the H of t impulse response on the input using a convolution, right? H of t convoluted with I of t. I of t in this case is step input U of t. Okay, so let's write this convolution as an integral in this way: minus infinity to infinity h of tau U of t minus tau d tau. Okay, so let's look at what each of these term means here. H of tau, so I am going to draw all of this as a function of tau. Okay, so h of tau is just a exponentially decaying function. Okay, a e power minus t by tau naught, and it's 0 before tau is 0. Okay, because there is a unit step function over there. And then U of t minus tau. Now this is a function of tau, so time is reversed. It's a step function, and time is reversed, so it's in this way, and it drops to 0 at tau is t. So this case is t less than 0 and U of t minus tau. Similarly, if you look at U of t minus tau, when t is greater than 0, okay, it's this function. Essentially, it remains 1 until it reaches the value of t. Okay, now this becomes useful to find this integral, because now you notice whenever t is less than 0, these two functions do not overlap, hence their product is 0, right? So this integral is 0. Just give me a minute. Okay, notice that the product of these two functions, before tau is t less than 0, this function is 0, right? So the product of the two functions is 0 when t is less than 0. When t is greater than 0, okay, this function is 0 till this point, that is from minus infinity to 0 it's 0, and this function is 0 beyond t is greater than 0. So the integral starts from this point 0, goes till this point t. Okay, h of tau is a e power minus tau by tau naught d tau. We already accounted for the u of t in the split. Okay, so this integral becomes minus a tau naught e power minus t by tau naught minus 1. And here we know a, which is 34, and tau naught, which is 3 milliseconds, and we want to evaluate this function when t is 5 milliseconds. So tau naught is in milliseconds, t is in milliseconds, so we can keep things as such, and this value turns out to be 82.7 millivolts. Okay, but we notice the question says the cell is being injected with current I. Okay, so the potential inside that should become more and more negative starting from 0. So the correct answer is minus 82.7 millivolts. Question number 1 from General Aptitude. Rajiv Gandhi Khel Ratna Award was conferred dash Mary Kom. The proposition that follows confer is always on. So conferred on Mary Kom, a 6-time world champion in boxing. Recently in a ceremony dash the Rashtrapati Bhavan, the president's official residence in New Delhi. Okay, so because Rashtrapati Bhavan is a specific place, okay, the proposition that fills the space is at and it's not in. And as far as this one goes, choices like, conferred to, conferred with, they confuse, or they are also tempting answers, right? So the best way to prepare for these type of propositions is to be aware of some abnormal word preposition combinations that show up in GATE exams. I have given a short list here. Second question. Despite a string of poor performances, the chances of KL Rahul's selection in the team are dash. So it says despite a string of poor performances. So that means despite that, chances are high, right? That's what the statement means. So the chances aren't slim. Chances could be bright, that's a possibility. The chances are obvious. Chance and obvious don't go well together, okay? And of course, they intend to mean the chances are high, so uncertainty doesn't fit. So the right answer is bright. Third question, select the word that fits the right analogy. Cover, uncover, associate, dash, okay? So given associate, we want to find the antonym. So for cover, uncover is the antonym. So we need to find the antonym for associate. So now unassociate, inassociate, perhaps even misassociate, they are all tempting. But the right answer here is dissociate, okay, choice D. Fourth question. So it's a question on inferring a text. So I'm going to read the text to keep track of time and all that. Hit by floods, the Kharif, in brackets, summer zone, crops in various parts of the country have been affected. Officials believe that the loss in production of the Kharif crops can be recovered in the output of the Rabi, winter zone crops, so that the country can achieve its food grain production target of 291 million tons in the crop year 2019-20, July to June. They are hopeful that good rains in July-August will help the soil retain moisture for a longer period, helping winter zone crops such as beet and pulses during the November-February period. Okay, given this, which of the following statements can be inferred from the given passage? The officials declared that the officials believe something and they are hopeful of something, so they don't declare. Option A is not the correct answer. Officials want the food grain production target to be met by November-February period. So they are talking about some natural event, right? Officials can want it, but they cannot really demand it from the nature. Want doesn't fit the text. So let's go to option C. Officials feel that food grain production target cannot be met due to the floods. No, the text said even though the summer things failed, in winter we have the possibility of meeting it. So it's not cannot be met as doesn't fit. So let's also take a look at the last option D. Officials hope that food grain production target will be met due to a good rabi produce. Yes, the officials hope that the food grain production target will be met due to good rabi produce. So the correct answer here is choice D. Fifth question. The difference between the sum of the first two n natural numbers and the sum of the first n odd natural numbers is dash. We have the sum of the first two n natural numbers. In that we have to subtract the sum of the first n odd natural numbers. So we have 1, 3, 5 till 2n minus 1. Okay, so up to 2n there are n odd numbers, n even numbers. So we have all the n odd numbers here in the bottom right. So when we take the difference between the two, of course the following terms cancel: 3, 3, 3, 5, 5. Similarly 2n minus 1, 2n minus 1. So what we are left with is 2 plus 4 plus 6 till 2n. Okay, that is 2 times 1 plus 2 plus 3 till n. Okay, so at this stage you could write this as n into n plus 1 by 2. If you don't know that, you could write this sum as, okay, so we have this series is repeated twice. So I am going to write the series in the reverse order: n plus n minus 1 plus n minus 2 till 1. Okay, so I wrote it again here, so I am going to remove this 2. Now this becomes, sum of the first two terms is n plus 1. Sum of these two terms is n plus 1. So how many such n plus 1s are here? 1, 2, 3 till n. So the answer is n square plus n, which is option B. Sixth question, again it's on inference from a text. Repo rate is at the rate at which Reserve Bank of India lends commercial banks, and the reverse repo rate is the rate at which RBI borrows money from commercial banks. Which of the following statements can be inferred from the above passage? Okay, what they are saying is repo rate is like the loan interest for the RBI banks, right? So if the loan interest rate decreases, decrease in repo rate will increase cost of borrowing? No. Increasing repo rate will decrease cost of borrowing? No. Increase in repo rate will decrease cost of borrowing? No. Decrease in repo rate will decrease cost of borrowing? Yes. And increase lending by commercial banks? Perhaps if they borrow a lot, they are going to also lend a lot. So the right answer here is option D. Seventh question. This is a seating arrangement question. I suggest you pause the video and try the question yourself. P, Q, R, S, T, U, V and W are seated around a circular table. Some conditions on how they are seated are given. Specifically 4 conditions are given. So I have drawn some seating arrangement so that I can fill it up very fast. Okay. So the first condition, S is seated opposite to W. So let me pick S is over here, then W is seated over here. U is seated at the second place to the right of R. At this point we notice right and left starts mattering. So the right of S is in this side. So anything anti-clockwise is to the right. Okay. And of course the clockwise direction is the left. So with that, let's go back to condition 2. U is seated at the second place to the right of R. Second place to the right of R, but we don't know where the R is. Okay, so given that, the third condition is T is seated at the third place to the left of R. Again, we don't know where R is. Okay, so let's try to find the positions where it's possible to seat R. That is, can R sit here, 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 here and here? Can you find which of these positions can R be seated? U is seated at the second place to the right. Is R seating here possible? No, because P is seated at the third position to R. So this is not possible for R. Is this possible for R? No. Two positions to the right of that is yes, already taken. That should be U. So this position is not possible for R. How about this position? Two positions to the right of it is free, and three positions, 1, 2, 3, three positions to the left of it is also free. So this is a possible position for R. And let's look at it. Are two positions to the right of R free? Yes. So that's a possibility. Or three positions to the left of R free? 1, 2, 3. No, that's not free. So this is not possible. Let's take this case. Two positions to the right of R, is it free? No, that's not free. It's occupied by W. So this is not possible. And how about this case? Two positions to the right of this is free. Three positions to the left of it, 1, 2, 3. That's also free. So this again is a possible configuration. So we recognize R can be either seated here or here. So I'm going to fill up two cases corresponding to that. We have S and W here. There's one possibility of R over here. S and W over here. Another possibility of R being here. So now let's go back to the U and T positions. Okay. So if R is over here, U is going to be over here, and T is going to be 1, 2, 3. T is going to be here. In this case, R two positions to the right. So U will be here. T will be three positions to the left. 1, 2, 3. T will be here. Okay. And V is a neighbor of S. So finally, so V will be here. V needs to be here. Okay. So now let's look at the possible choices. P is a neighbor of R. Okay. P can be either here or here. Similarly, here P can be here or here. So not necessarily. Q is a neighbor of R. Again, Q can be here or here, here or here. So not necessarily. Okay. P is not seated opposite to Q. If P were here, Q need to be here. Similarly, if P were here, Q need to be here. So in either case, whether P is here or here, here or here, Q won't be opposite to Q. So this is the right answer. And just to verify, R is the left neighbor of S. R is the left neighbor of S, not necessarily. Okay. So in this case, R is not necessarily the left neighbor of S. Okay, so the right answer is choice C for this one. Eighth question. The distance between Delhi and Agra is 233 kilometers. A car P started traveling from Delhi to Agra, and another car Q started from Agra to Delhi along the same road 1 hour after the car P started. The two cars crossed each other 75 minutes after the car Q started. Both cars were traveling at same speed. The speed of car P was 10 km per hour more than the speed of car Q. How many kilometers the car Q had traveled when the cars crossed each other? Okay, so this is a simple problem on speed, distance and time. So let's convert the text into equations. Then that should give the answers. Okay, so we have Delhi and Agra here. Car P starts from Delhi, goes towards Agra. Car Q starts from Agra, goes towards Delhi, and they meet somewhere. They travel on the road, same road, and they meet somewhere along the road. So Q starts 1 hour later, and they meet. Both the cars meet, say, somewhere over here. They meet 75 minutes after Q had started. So the amount of time that Q travels on the road is 75 minutes, which is 1.25 hours. And the amount of time that P travels to this point is 75 minutes plus 1. So that's 1.25 hours plus 1. So 2.25 hours. And let's call distance to be x and this distance to be 233 minus x, because the total is 233. Okay. And speed of car P, the speed at which car P travels is 10 times higher than that of speed of car Q, right? So if the speed is S, this is S plus 10 here. Okay, we need to find X, right? So let's write down, convert all this information into equations. First thing, distance by time is speed, right? Distance by time is speed, basic relation. That means 233 minus x by the time it travels, 2.25 is s plus 10. That's one equation. Second, x by 1.25, that is speed of q, that is s. So let's eliminate x from this equation. So now x is 1.25 s, right? Now using this we can solve for s. I think that turns out to be 60.14 kilometers per hour, and this implies x is 75.2 kilometers. So the option is B, that's the correct answer. Ninth question, for a matrix M equal to Mij, I and j runs from 1 to 4, the diagonal elements are all 0 and Mij is minus Mji. The minimum number of elements required to fully specify the matrices. Okay, so we have, let's say this is the matrix, it's a 4 by 4 matrix because I and j runs from 1 to 4. All the diagonals are all 0. So we have 0, 0, 0, 0, and we have an additional condition which says Mij is minus Mji. Let's take I equal to 1 and j is 2. So M12, we know that M21 is negative of minus of M12, minus M12. So the moment we know what is M12, we know what this matrix is, sorry, this element is, that is minus M12. Similarly, M13 here, minus M13 here, okay, M14 here, minus M14 here, and M23 and minus M23, M24 minus M24, M34 minus M34. So if you notice, this lower triangle depends on just the values of the upper triangle. So the number of elements we need to specify is 1, 2, 3, 4, 5 and 6. So 6 is the correct answer, and that's option B. Last question from general aptitude. The profit shares of two companies P and Q are shown in the figure. If the two companies have invested a fixed and equal amount every year, let's say 100, then the ratio of the total revenue of company P to the total revenue of company Q during 2018 to 2018 is, okay, so what we are given is profit percentage. Revenue is profit plus expenses. Let's say that invested expenses like 100 every year. We need to find the ratio between P and Q. Okay, so the first thing we have revenue, right, which is what we want, that is profit plus expense or investment, okay, that is investment. Okay, so let's make this fixed amount 100 every year. Now all we need to do is to sum up all the revenues for P and divided that by sum up all the revenues for Q, okay, that is 110 in 2013 for P plus 120 plus 140 plus 140 plus 150 plus 140. Divide that by revenues for Q, which are 120 in year 2013 plus 130 plus 130 plus 150 plus 160 plus 160. Okay, this turns out to be 800 or 850, and these are in the ratio 16 by 17. And the correct answer is option B. Leave comments on how you would approach the problem, whether you think the problem is easy or hard or difficult. A person in standing position flexes hip by 50 degrees from the initial trochanter knee line. This is the trochanter knee line. Flexes hip by 50 degrees, right? And then flexes knee by 20 degrees. This is incorrect. Flexes hip by 50 degrees and then flexes knee by 20 degrees.